Yeah, well, I guess it's a mixed blessing that it's so incredibly hot outside, draws you inside to the air conditioning here and coming inside. Um, I've I've been here for 20 years, and raised my family on the Near East side of Madison. So we come out to Monona a lot, to Aldo Leopold Nature Center a lot, and so it's really a pleasure to be back here in this beautiful location and sharing some work with you. But anyways, so yeah, I'm a paleoecologist, which is sort of a strange word, but I'm basically study past ecosystems and species responses to past environmental change. As I'll show you in a few moments, there's been a lot of environmental change that species have adapted to, sometimes failed to adapt to, but there's lots of ways we can learn lessons about how species respond to changing environments and ways we might help them. So just to kind of set the stage to begin with here of course is beautiful Madison today on a sort of lovely summer day like today, a good day to be at or by the lake. So now here's a picture of Madison, a hypothetical picture of Madison. This is not a real photo of Madison. This is a photo from Iceland. But this is what Madison might have looked like 20,000 years ago, at the height of the last ice age, right? And this is, 20,000 years ago is very long in human timescales. That seems like forever. That's prior to various ancient civilizations and so forth, but it's an eye blink in geological time and evolutionary time. And so from the perspective of the species we see around us, most to all of them would have lived through these past environmental changes. And this ice sheet that would have been at its sort of southern extent here in Wisconsin, the famous Ice Age Trail running along the margins of that ice sheet, extending all the way across Canada, a 3-kilometer thick ice sheet. That ice sheet grew in response to global temperatures that were about 6 degrees Celsius, 11 Fahrenheit, colder than today. And so it's a small number. 6 degrees Celsius grows a 3-kilometer ice sheet. Here's Madison 14,000 years ago. Large animals dotting the landscape, mastodons and ground sloths and camels, all these animals, the Pleistocene megafauna that went extinct with the end of the last ice age due to some combination of changing environments, changing climates, and human arrival and pressures on these species. And at this point, global temperatures are maybe 1.5 degrees colder than present. This is sort of the warming point. And we have these bogs and spruces and ash trees and these weird mixtures on the landscape. So some of the big takeaways as we start to kind of dive into this kind of data, I'll kind of sum this at the beginning, sum this at the end, is that we can see that there were profound changes from the last ice age today, both in the cryosphere, the ice sheets, and they're melting away, and the biosphere, all the species changing their distributions, changing their diversity in response to a 4 to 6 degree global warming with the end of the last ice age. We will see that over and over again, there's this story of ecosystem transformation. The species that live around us now were not the species that lived here in abundance 20,000 years ago. At the same time, most species make it through. The megafauna are the big exception. They mostly don't make it through, but most of the plants around us did make it through. And so there's an innate adaptive capacity of species to adapt to changing climates, and that's good news. Sorry. Climate resilient landscapes, like much of southwestern Wisconsin. I give this talk to different audiences, and I didn't change that one. But Iowa, too, we love Iowa, are essential for stewarding biodiversity and climate adaptation. The driftless area in particular, which spans that area, is a really important region. And we can help species adapt in various ways. Most importantly is slow down rates of climate change. The less fossil fuels we burn, the less climate change happens, the slower it happens, the better that is for species. But given the reality that climates are changing now and will continue to change for some period of time, there are other things we could do to accelerate rates of adaptation to these changing climates. So to kind of set the structure here, I'll give a bit of an intro, talking about the last ice age and some of the big picture aspects of it, a little bit about how we study the past, how do we know what we know about the past, then some of the lessons learned and implications going forward. So here's a kind of a starting figure, and there's a lot going on here, but it's really useful and important. And by the way, can people see in the back? Is it enough contrast for you all back there? Yeah, okay, great. So the vertical scale first, this is changes in temperature, delta temperature in Celsius, and it's all relative to the late 20th century. So anything that's positive would mean warmer than present, or warmer than late 20th century. Anything negative would be colder than the late 20th century. It's all anomalies, all differences from the recent past. So this is a global temperature, a global temperature curve we're looking at. And then this is time here, and time is going to change because we're going over a very long period of time here. So we start at 65 million years ago, and that's when the dinosaurs went extinct. So this is the age of the mammals that we're looking at here, the Cenozoic. And then we go for tens of millions of years to millions of years to the last several 100,000 years to the last 20,000 years to the 20th century and into the 21st century here. So this part right here is the instrumental record. This is what we have from weather stations and our weather balloons and our modern science. These are climate model scenarios of where we might go in the future, depending on how much fossil fuels we burn, and the climate model scenarios of how much the world would warm in response to our fossil fuel burning. And then everything back here, this is all from the past. This is all what we use, different proxies, different geological records to study and recover. And one thing that's amazing is that we have a very well-developed global temperature curve. We know pretty well what the history of global temperatures were like over this time period. And you can see that some of the big patterns here, one is that there's this long-term cooling that at the age of the dinosaurs, that's a time in which we have crocodiles in Greenland. We have these sort of very warm systems all over the world. There's no ice, as far as you can tell, and no permanent ice anywhere in the world. And then over this sort of long period of time, over this sort of 60, 50 million years, there's a cooling of about 10 degrees or more worldwide. So you go from what we call a greenhouse state of the climate system to an icehouse state of the climate system. Ice sheets begin forming around Antarctica first, around maybe 40 million years ago, and then around maybe 3 million years ago, the northern hemisphere starts to glaciate, Greenland and so forth here. So as the world cools, the ice sheets start to form. And then we start to get in these bigger and bigger swings. As the ice sheets kind of wax and wane, temperatures rise and fall, and these are the ice ages. And now we start to see these swings here, and over the last million years or so, there's been these big swings. Every time we get down to a low like this, we have an ice sheet on top of us here, on top of Canada and on top of northern Wisconsin. These are the glacial periods. And then we get to the interglacial, these brief warm periods that are maybe similar to today or maybe a little bit warmer than today by about a degree or so. And then we have the next swing, these sort of 100,000 year cycles that go back and forth. And during this time of major back and forth, ice sheets melting and retreating and advancing over North America, back and forth, humans evolve as a species. And our species arrives around 100 and 200,000 years ago. And so this is the range of climates that our species has experienced over this time period here. I'm going to talk a lot about this time period forward, the last ice age, that was actually called the Wisconsin Ice Age, named after all the landforms, glacial landforms in the state here. The Wisconsin Ice Age, which was about 5 degrees colder than present, this global warming of about 5 degrees or so, 5 or 6 degrees, and then we have a period of quote-unquote relative climate stability over the last 10,000 years, continuing through the 20th century. And this is when we have agricultural societies forming, and all of our modern civilization is based upon this range of climate variation. So one of the things you can start to see right away is that, good news, there has been lots of climate variation in the past, and every species around us has evolved under these past changing climates, so there's some adaptive capacity out there. But bad news, most of our human society has not seen this, right? We've worked in this space here, and now we're being asked to adapt to and confront these changes coming like that. Okay, so most of the talk I'm going to do kind of going forward here is going to really focus on this time period here, the last ice age 20,000 years ago to today. And by the way, I'll take questions as we go. I'm throwing information at folks. Yeah, right there.
Why did it cool so much? What caused the cooling?
Yeah, I mean, as always, the Earth is big and complex. There's probably multiple things. But the short answer is that global CO2 is going down at the same time. So carbon dioxide, a greenhouse gas, really is like a global thermostat. If we have high CO2 in the atmosphere, the high concentrations, temperatures are high. And then as carbon dioxide levels drop in the atmosphere, temperatures drop as well. So there's very strong evidence from geology that greenhouse gases like CO2 really matter for global temperatures. The next question would be, why did CO2 drop over this time period? And that actually, at these time scales, rates of rock weathering matter. Like how fast mountains crumble away, those chemical reactions as rocks kind of dissolve away consume carbon dioxide from the atmosphere. So there's some silicate carbon feedback loops that don't matter on our time scales. They're really slow, but these sort of tens of millions of time scales, they really matter a lot. So yeah. Question in the back and then there. Yeah.
Why were there such
The ice age is so right. So at different time scales, different things are controlling climate variability. At these time scales, it's changes in the Earth's orbit. As we go around the sun year after year, not much changes. But every 20,000 years and every 100,000 years, we wobble a little bit. The eccentricity of the Earth's orbit changes a little bit, and that changes the amount of sunlight we get at different latitudes. And that change in sunlight is just enough to kind of melt away these ice sheets and trigger these big changes in the climate system. So it's silicate silicate weathering at these time scales and Earth's orbit at these time scales. Yeah, there.
How do we know what was the temperature back in this?
Yeah, that's a great question, and I have a whole class on this at UW Madison called 335. Senior auditors welcome. But the short, let me hold that thought because I'm going to talk about studying the past a little bit, and I'll talk a little bit more about that there. Yeah.
I just wanted to point out that the Holocene, the second portion of that, is really expanded out.
Yeah.
And it's really just a little short period. It would
Yeah.
be
Yeah, thank you for pointing that out. I mean, there's pros and cons to showing the data this way, because you can sort of look at different things at the same time. But it does trick you because basically this thing that's kind of expanded out here is the same length as one of these here. So you get a little fooled by that. So thanks for calling attention to that. Okay, so just now kind of focusing on this sort of 20,000 year period, it's been a long-term sort of classic period of study for paleoclimatologists and paleoecologists, because paleoclimatologists want to understand, why does the climate system vary so much and what are the drivers, and paleoecologists want to understand what are the effects of those climate changes on ecosystems and species and so forth. And so, this is the state of the world at the last ice age, 20,000 years ago. Ice across North America down into northern Wisconsin, ice across Fendo-Scandinavia, covering Great Britain and so forth. So the northern hemisphere is very, very much glaciated. As far south as about 43 degrees north. And then this is the state of the system today. There's just permanent ice on Greenland, there's sea ice on the Arctic Ocean, but that's it. So it's a very different state of the system. So, the how do we know question. So here is one of our most important sets of proxies about how do we know past climates are ice cores. Ice cores are really important in paleoclimatology because they have two useful things. They have little pockets of air in the ice, and those little pockets of air, as that ice builds up over tens of thousands of years, are little capsules, little samples of atmospheric composition at those different time periods in the past. And so from ice cores, we can get records like the yellow circles. The yellow circles is showing a rise in carbon dioxide over the last 20,000 years. And to help you get oriented a little bit, the time scale here is from 22,000 years ago to 7,000 years ago. And we often talk about age before present. So this is 22,000 years ago, 20,000 years ago, and KYR, K stands for kilo, for thousand. So this is thousands of years ago. So you can see from our ice cores and the bubbles that people have analyzed in those ice cores that carbon dioxide was low, about 200 parts per million, and then it rises, plateaus a little bit, rises, and each one of these rises and plateaus people have written lots of papers about to try to understand what's going on here. And then the red and the blue curves are temperature reconstructions. The red temperature reconstruction is from the ice core itself, because there's water isotopes and things, oxygen isotopes they can use to reconstruct temperature. The blue curve is a global network of temperature records all around the world averaged together. And what you can sort of see here is that CO2 and Antarctic temperatures are pretty close to each other. They're kind of tracking closely, but global temperatures lag. They follow the CO2 rise. So this is one of our pieces of evidence that when carbon dioxide glows up, after some period of time, global temperatures goes up. And this becomes sort of a cause and effect kind of analysis. Now, it might be coincidence, there could be other things going on, but one thing you can say is that the CO2 goes first, so it's not likely that this caused this, it's more likely that this caused that, because the temporal order would happen first. So with that global temperature rise, and with all that ice that was a 3 kilometer thick ice sheet on top of the oceans, all that ice goes into, that 3 kilometer thick ice sheet, all that water that melts goes into the world oceans. And so what you're seeing here is a map of what the world would have looked like 20,000 years ago, where we have, again, the ice sheets there in white. And then, the light tan are places that are land masses today. The dark brown are places that were land masses 20,000 years ago. They've all been flooded since then by that rising sea level. Sea level rose by about 400 feet from the last ice age to present. It's shocking, right? I mean, we are worried about millimeters to feet of sea level rise now, and it was 400 feet from the last ice age to present. So it is really a lesson of the things that can happen when things get warm and ice sheets melt away. And it really has big effects on the biogeography and ecology, right? At the last ice age, Australia and New Guinea were one landmass. Species and people can move back and forth. Species and people can move through here. You may have heard of the small humans that were been found in here. This would have been a highway for people back in those times. And so there's just a different kind of connectivity. Vice versa, Alaska would have been cut off from the lower 48 by the ice sheets. And so things that are connected now or connected then aren't connected now, and vice versa. There's big changes that go with this. And this relates to, again, sort of painting the picture and all things happening during this time period. Humans arrived in the Americas during this time period as well. There's more and more science, more and more work all the time. And, what you might have learned in school, say, a while back was that, Clovis first, that humans arrived in the Americas, say 13,000 years ago, and they developed this sort of big game toolkit of these big spear points and so forth. Now we know that, sure, the spear points were around 13,000 years ago, but humans were probably in the Americas at least by 15,000 years ago. Now the best site out there suggests 20,000 years ago. So people have been in the Americas for a while, and they're arriving at the last ice age. And there's this now kind of new iconic site, White Sands, New Mexico, where they have footprints and trackways of humans and big animals together, all in the same locality. So okay, so that's kind of that's sort of this, giving you a sense of these big sweeping changes that happened during this time period, all linked to this sort of rise in CO2 and 6-degree global warming. So how do we study the past? So if you're an ecologist like myself, there's a wealth of different information that you have. You have big bones that people might dig out of their backyard, if they're ditching somewhere. You have microfossils, which is the kind of work that I mostly do, where you find in lakes and bogs little pollen grains or little diatom fossils, little aquatic organisms. The pollen can be identified to different plant species. Right now, the big thing that everybody's working on more and more is ancient DNA, getting DNA out of the muds of the past, and that can tell you what kind of species were around there by matching those fragments of DNA to modern libraries of modern species. And then the written record, the oral record, and so forth. When it comes to lakes, which is what I work on, there's lots of lakes around here. It makes sense. I'm based in Wisconsin working on lakes. Lakes are, they are steadily accumulating mud at the bottom. These lakes have been around ever since the ice pulled away, melted away, and so they've been around for 15,000 years, give or take. And that mud is just sort of steadily accumulating. As long as that lake is there, as long as it doesn't dry out and desiccate, that mud will just keep accumulating. And it's maybe a centimeter every 10 years. And so, a few thousand years more, and those lakes will start to fill up. And there you can see places where lakes have become bogs, and that will happen over time. But most of the lakes around here are still young enough that they haven't filled up yet. And so, a lake like Mendota, might be 20 meters deep, and it might have 10 or 15 meters of mud below that. And so that becomes our archive, our record, that we can go out, we anchor in, we sort of push our way down, kind of meter by meter, and then we bring them, we can sort of see, we sort of wrap up the tube in the PVC, and then we bring it back, and here's like one section of mud that we've collected. And so we can then bring back these cores back to our labs and analyze them. And they are kind of, the treasure troves, the trash cans, they're just sort of collecting everything that's in the lake or in the watershed around the lake that's then washing into the lake. And so the pollen that's mostly blowing in from, if you have, everybody here has their seasonal allergies, there's a lot of pollen in the air. So all the pollen just kind of settles onto the lake and falls down through the water column and gets captured. That tells you what kind of plants lived around the lake. Charcoal washing into the lake tells you how often fires were happening around that lake. We use radiocarbon dating to figure out how old those sediments are. Ancient DNA is a new technique for detecting potentially almost anything. And then all these other kind of geochemical markers, organic geochemical markers that all tell us different things about past environments and past temperatures. So there's a whole, and the way my field works is that I'm a pollen guy, somebody else would be an isotope person, somebody else would be a biomarker person. We all kind of work together in teams, each one of which has their own specialized lab facility to work on this. We're inherently a team-based science to kind of work on these records together. And getting back to the question about, well, how do we know past climates at that far back? Ice cores is one of the big ones, but the other big one is marine cores, ocean sediment cores. And just like we can core lakes and go back 20,000 years, there are big drilling vessels that can recover ocean sediment cores that go back tens of millions of years. And if you read the New York Times, there's been an article that the US drilling ship, the JOIDES Resolution, is just getting decommissioned right now. So my community is very unhappy about that. We just lost our capacity to do these kind of big long-term paleoclimatic changes. So that's how we study the past briefly. And then people have been doing this kind of work for decades now. And it's typically a site at a time, a couple sites at a time, a scientific paper at a time. But this has been going on for decades. And so now we have lakes all over Wisconsin and all over the upper Midwest and all over the world where people have been doing this kind of work. So every triangle here is a place where there is a fossil pollen record. Somebody has gone out and cored a lake and recovered the pollen from it. And then I'll show you some more things in a moment. This is now gathered in the Neotoma Paleoecology Database, which is a global resource that we use to gather this kind of data together. Okay, so that's quickly how we study the past. I'm happy to talk more about that. But let's see kind of what we've learned. What are some of the takeaways here? Well, the first thing I want to kind of show you here is one site, one example of a record, and this is Devil's Lake, which everybody knows Devil's Lake is one of the iconic sites in Wisconsin here. Lou Marr from UW-Madison and then a follow-up team in the 2000s have taken sediment cores. They've anchored in and retrieved sediment cores from Devil's Lake, and then worked up the pollen record to get at the vegetation and history at Devil's Lake. And so now we have to think about time on the vertical axis, because this is the way geologists think about time a lot, because as sediments deposit, the older sediments are at the bottom and the younger sediments are at top. And so here, this sediment core is 14,000 years old at the bottom and then 0 years old at the top. It goes all the way from 14,000 years ago to today. And so time is going up. And then we're looking at here is different plant taxa: spruce, pine, oak, elm, poplar, birch. And then we'll talk about charcoal over there in a moment. And we're looking at the changing abundance of these plant taxa based upon the pollen that we find in the sediments here. So at the beginning, when 14,000 years ago, when there's still ice in the area, we see lots of spruce trees around Devil's Lake. It is a boreal forest, like you'd see in the North Woods today. Then as temperatures start to rise, and by the way, this period here, so kind of 14 to 8,000 years ago, this is when that kind of 6-degree global warming is happening. And so what we're starting to see as we kind of go through here is temperature, climate-driven ecological change. And we see the complete loss of one forest. These trees, these spruce trees die out. They become less abundant to not present at Devil's Lake. And then they're replaced by pine. Pine forest becomes super abundant. So we have an ecosystem transformation here. And then we have another ecosystem forming there. And then the pine forests are still there, but more and more oak moves in, and elm. And so you start to get these deciduous forests, these mixed forests here. And this is all being driven by changing climates, rising temperatures, as some species die out and other species expand and become more abundant. And this is very analogous to what we think will be happening today. And then we have more changes over time. Over this sort of last 10,000 years, temperature changes become smaller, but changes in rainfall become bigger. So there's probably times here where it gets a bit drier, a bit wetter, and that leads us to changes in oak forest versus oak savanna, high fire activity versus low fire activity, and so forth. So that's just one site where we see these sort of 4 major ecosystem transformations over this sort of 15,000 year period. So, all right, now, there we are. All right, so what I want to do now, that was one site to give you a sense of what's happened at one site here. Now what I want to do is show an animation here that's going to be showing many sites. And just to kind of, before I start the play here, just to get you oriented here, we're going to start 21,000 years ago. At 21,000 years ago, the light blue is ice covering North America. And you're going to watch that ice kind of melt away as temperatures rise. And then all the different circles are different taxa of shown over here, spruce and elm and so forth. There's a lot to see here, but I'm going to focus your attention here on the east, where you're going to see blue, that's spruce, and then red, that's oak. And what you're going to see here is lots of spruce down here dying out, spruce expanding here and expanding northwards. You're going to see this climate-driven range shift of spruce and then oak kind of filling in behind it here. You're watching the circles change. You start to see less blue down here. Spruce is dying out down here. Spruce is expanding across this whole area here. And it starts to die out. More red and oak is filling in. Spruce is filling in here, right? Okay, so I mean, some of the big takeaways here as you kind of watch this again is that when climates change, species move, even trees move. You know, the trees aren't walking, they're dying out, but their seeds are being dispersed to new locations. Those populations seed and start up new populations. There's places where either spruce is dying out because of direct heat stress or it's getting outcompeted by oak and other species, but given a strong enough climate forcing of 6 degrees and given enough time, you can have this wholesale continental scale range shift. And it is very analogous to the way that birds migrate north and south with the seasons. Trees migrate north and south with the ice ages. It is a very similar kind of process on a different time scale.
So,
Yeah.
so did the tree population increase as the climate warmed?
I mean, overall, North America gains land area, right? So there's more places for trees now than there was 20,000 years ago. In general, some species become more abundant, some become less abundant. It's complex. Each species is a little different here. And just to kind of show you some of that complexity, here's sort of static maps for spruce and ash. We sort of spatially gridded and interpolated so you can not get caught up by all the dots, but kind of get the broad pattern here. And you can see spruce is a simple story of migrating north, dying out in the south and expanding to the north, whereas ash is more complicated. It's not very abundant here. It becomes really abundant during this sort of intermediate time period and then becomes less abundant again. So each species is kind of following its own trajectory. And one of the other key lessons is this, what we call species responding individualistically to climate change. They're not moving as intact forests and as intact units. Each species is kind of doing its own thing, moving its own rate, its own direction, and so forth. And so we see this reshuffling in the past, and again, we expect this reshuffling to happen today. Spruce and ash were kind of living together in the past, although not so much ash. They were very abundant together here, and then now we think of ash as being in southern Wisconsin around here, and spruce being in northern Wisconsin. So now they have separate ranges, but back then they lived quite happily together. So things mix over time. Another big lesson is, how fast does this happen, right? That's really important, right? We are warming the world at unprecedented rates. It is really fast what we're doing right now. But there are occasional examples where we can find locally or regionally fast climate changes. One of the ones that in my field we call the Bowling-Allarod warming. It is 5 or 6 degrees in a few decades. It is really warm, really fast. But it's not global. It's a North Atlantic and Europe and maybe parts of the eastern US warming. Here's an instance of it where we're going up in time, and right here there's a step change in temperature. This is a proxy for temperature here, and there's this kind of very abrupt change here. And then this is a site in the Alps of Switzerland, and you can see that temperatures rise by a few degrees, and then within a decade the ecosystem changes. So this is a fast vegetation response, and we go from a sort of a sage, sedge, tundra to juniper filling in right away. And these are probably all plant species that were living locally in that area. And so some become more abundant, some become less abundant, but they're not having to move huge ranges. They're all just there, and the local dominance change very quickly in response to that step change in temperature. But then over here, we see that this does take centuries because some species aren't at that site and they have to move to that site, and that takes a while. So birch, it's maybe a 200-year time lag between the warming and when birch becomes abundant, and then pine arrives about 800 years later because pine was probably not at that site in the northern Alps. Pine was probably somewhere in the southern Alps and had to throw a few seeds out, start a new population, throw a few seeds out, start a population, and it took a while for pine to get there. So this is this concept of migration lags, and that when we have rapid climate change, like we're having now and we had then, some species that can locally adapt quickly, but some species can take centuries to adapt if left to their own devices. And so this is where helping species adapt is one of the things we can do. So the other lesson is that plant extinctions are rare. We see very few plant extinctions in general during this time period. The one that we do have a good example of is that there's an extinct species of spruce called Picea critchfeldii. And these are all kind of needle cross sections. And these are the needle cross sections of needles recovered from those sites down there from sediments 20,000 years ago. And they look different from the needle cross sections of species today. And they're different enough that they've been classified as different species. So this is one documented instance of a species of spruce that lived 20,000 years ago that is no longer around today. But that is the exception and not the rule. Most species of plants make it through the global warming. But that contrasts with the big animals. There is a famous, sad extinctions of these big animals worldwide. And what this data shows is, first off, is how devastating it was. We lost 2/3 of our big animal genera worldwide during this time period here, between about 45,000 years ago and today. And what we're looking at here is the body size, so by continent. So for this continents, for Australia, South and North America, this size is body size in log grams, and the gray bars are the body sizes of the surviving mammals that made it through this time period, and then the red are the body sizes of the animals that went extinct. And what this shows you very clearly, this is a very size selective event. The big animals went extinct, and the small animals mostly made it through. And so this is, one of the reasons why big animals are of concern. And this is probably, to me, one of the signatures of climate change plus human activity being what sort of takes these animals out. They are, relatively easy to get, relatively easy, high resources and so forth. So it's this sort of synergistic effects that's probably key for these big animals, not climate change by itself. So to kind of summarize here, is this a big deal? When we've seen a 5-degree warming in the past, does a lot happen? Yes, a lot happens. How do species adapt or fail to adapt? We see that species move. We see that novel ecosystems emerge. We see some responses that are fast, some are slow, and that extinctions are rare for the plants, but very common for the big animals. So how are we doing on time, by the way? I don't have a watch on me.
It's 10 after 7.
Okay, all right, so a few more minutes, then we'll wrap up. So, okay, let's carry this forward to lessons. How do we take this information and translate it to action now? So how do species adapt or survive climate change? There are options. One option, kind of shown in the upper right there, is what I've been kind of talking you through, is that when climate change, species move. They migrate, just like birds migrate season by season. Another option is that species can persist in little microhats and little refugia, little places where they have a little favorable climate that works for them that they can hang out in until the next ice age ends or begins, whatever their preference is. They can adapt, and my favorite story is the wood rat. The wood rat, there were big wood rats at the last ice age, and they are small wood rats now. It's maybe a 20% difference. It's not like hulking wood rats, but large body sizes are adaptive under colder temperatures, and so as temperature rises and falls, the wood rats get bigger and smaller, and they can adapt to that evolutionarily. And then, of course, sometimes they don't adapt, and that's what we're trying to prevent today. So this understanding that climates are changing now, that reality we have to deal with, and I would say from the geology perspective, the realism we've had it for a long time, the climates have changed a lot in the past, is moving kind of the field of conservation biology and land management away from what you might call the restoration paradigm, that there's a baseline, stable equilibrium for an ecosystem, something happens to it, like let's say it gets clear cut or whatever it might be, and you try to restore back to the way it was. In this era of climate change, that paradigm doesn't work so well anymore because we are on this trajectory where climates are going to be steadily changing for the coming decades, hopefully less. We try to slow that down, but there is climate change already underway and more coming for the coming decades. And so in that context, we have these sort of options. This is what the new paradigm we call RAD, resist, accept, direct. Resist is where you try to help species stay in their current state or slow the rate of transformation. And the kind of metaphor here, if the wind is pushing this way, if you're resisting, you're spending effort, you're spending energy to push against the wind and stay in place. Accept would be sort of accept and let things go and let things go where they will. And the metaphor, you're sort of drifting here and the wind pushes you wherever it pushes you. And then there's the direct. You sort of try to guide these ecosystems to some sort of state that you have some preference for whatever reason, beauty or economic services or whatever it might be. So things that we can do in this context then, as we sort of think about how we can help. So first, and the one that always is most important, is slow down climate change. The more we can move away from fossil fuels, the more we can move towards non-carbon energy sources, be more energy efficient. That slows down, or even ideally halts these current climate changes, and that buys time for species to adapt. The rate of change matters a lot, and slower change is better from an adaptation perspective. We can also work to accelerate rates of ecological and evolutionary change. We can try to help species adapt to the changes around them. We can try to protect key landscapes like the driftless area. And then, of course, I will always say do more science and learn more about the world around us. So I'm guessing, who here has seen this book or know of this book here? Oh, okay, one. So this is a great book. Go get it. Yeah. Actually, I think for an eco-action group, I think a reading group around this book would be really good. This came out a few years ago. It's maybe 5 or 6 years old, so maybe some of the information is a little outdated in it. But basically, this is a book where a private individual with resources at hand hired a team of analysts and said, what are all the ways that I can deal with climate change, and what are the most cost effective? Where do I get the most bang for my buck? And so it comes up with a list of 100 things you can do to deal with climate change and reduce your carbon footprint. And then it comes up with it's ranked by cost effectiveness, and there's like a top 10 list and so forth. So it's a great starting point for conversation, what you might do and so forth. So one thing is get the book, and I don't make any money off this. I just like this book a lot. And talk about climate change, have these conversations. Home insulation is always one of the first things that is a win-win. You save money, it's relatively low cost, you save energy. Switching away to electric vehicles, all this stuff this community knows. But still, these are the things to work on. Move yourself forward in these areas. And then, of course, having the political conversation as well, letting your elected leaders know that this is an important topic to you. And this sometimes, this is less true now, but 5 years ago, it sometimes felt not okay to talk about climate change. It felt unsafe depending on the context you're in, the company you're in. But it's important to have that conversation. So I do all the time, and so I encourage us to do as well. So, okay, so that's one, slow down the rates of climate change. And then another thing we can do is accelerate rates of adaptation. That species can adapt to climate change if it's not too fast. We can see species like spruce migrating northwards. And so one way to think about that is helping species move, because often species today, not only is it happening very quickly, which doesn't give them much time to move and disperse and throw seeds out and so forth, but now, of course, modern landscapes are so much more fragmented, right? There's big agricultural fields and parking lots and roadways and all the rest of that. So it's harder for species to move now than they used to, trees and birds and everything else. And so already, of course, there's studies like this one where there may be a few. This is an endangered species in New Zealand. They looked at where the existing populations are. Some of those existing populations have already gone extinct. And then they identified other places that might be suitable habitat for that. And so then it becomes this translocation or migration. And sometimes you do it even in the absence of climate change. If you're trying to protect a species of concern, you might move it to some new available habitat. But now increasingly, as climates change, people are thinking about and starting to move more and more towards helping species move northward or wherever else that might be favorable for them. And sometimes that's done in a management policy perspective, like the Forest Service, starting to plant more warm adapted species further northward. Sometimes it happens accidentally as people plant magnolia trees in their backyard in New England. Magnolia is not really native to New England. Historically, it's been too cold for magnolia. Magnolia is found more to the south in the southern U.S. But as temperatures rise and winters get less severe, now magnolias are sort of escaping out to the woods of New England here and are starting to expand their range. Now, this wasn't a policy decision, but it's had, from a climate adaptations perspective, it's helping magnolia expand its range at a faster rate than it would have been able to on its own. And then there's protecting key landscapes. And I think the good news here is that the landscapes that we often find the most beautiful, these kind of rugged, valleys and rivers and so forth, are also really good for protecting species because they have so many little microclimates. Whether you're close to a river or far from a river, if you're on the south side of a hill or on the north side of the hill, forested or not forested, these kind of microhabitats and microclimates are really good for protecting species. And they've been shown that to be hot spots of biodiversity and places where species have appeared to have ridden out and survived past glacial and interglacial cycles. And so, the driftless area, there's various, the Iowa Pleistocene snail and northern spoonbills. There's various endangered species with small ranges that are kind of preferentially concentrated in this driftless area because they've been kind of hanging out there over multiple glacial and interglacial cycles. And if you kind of think about why is the driftless area such a good area to protect species, it's not because it's been a stable climate regime. Changes have been as big there or bigger than anywhere else. It's had plenty of climate change, but it's got high topographic complexity that creates all these microclimates, and then it's got a high connectivity among habitats. So species don't have to move across the US the way that spruce was. They can move at much smaller scales and move among patches and survive that way. So it's really important for species biodiversity protection. And then doing more science. Matt Damon and the hero botanist, one of my favorite scientific characters, surviving on Mars through his know-how. He's going to have to science the heck out of this. And so that's part of what my part of the job is, right? To kind of help do more science and bring more knowledge to bear. And so this idea where the more we can understand past climates and how those have changed over time, how they're changing now, the more we can understand how species have adapted to and responded to those climate changes, well then the ultimate goal is to build our better predictive ability, ecological forecasting. How well can we forecast near-term or longer-term responses to the changes around us and use that to guide decision-making and so forth. And in this era, there's more and more data all the time and more databases being brought to bear. And so here is GBIF, the Global Biodiversity Information Facility. Every dot there is some species that's been recorded by some individual at some point in time. There are now, I don't know, tens of millions or more of observations in GBIF. So we have these incredible databases of species distributions and diversity. And you can also see spots that are more or less sampled there. Of course, citizen science is great, and I have colleagues who work with citizen science data sets all the time. So if you're ever part of this, iNaturalist or eBird or other projects like that, that really does pipeline to ecologists working with this data. It's super helpful and really encourage people to engage in these projects. And then kind of, again, my piece of the puzzle, I am part of a community that is really working to gather all of our lake sediment cores and bugs and all these different things we observe about the past and stitching those together into global databases so we can make data, animations like Range Mapper, we can look at global changes in biodiversity and so forth. And that's an open resource called Neotoma. And if you ever wanted to play with that, shoot me an email. I can give you some pointers and tips about how to access some of the data there. And then just one last thing, I don't have internet here. I was going to do a little demo here, but just kind of like a resource if you haven't seen this yet. This is a good one about what will climate feel like 60 years from now. And this is called Climate Analog Mapper. Here's the URL for it. You can basically click on any location, any one of these cities here, and it'll tell you what the climates of the future, the best analog for the climates of the future will be. So if you click here on Madison, the best future analog by the end of the century is Pawnee, Oklahoma, right? Which is, you think it's warm now? Just wait. Yeah. So, yes. And so this is a very place-based. We all have some place that's dear to our hearts, and we can start to get a sense of this abstract. What does a 5-degree temperature change mean? Converted into sort of a geographic equivalent. Another resource, and this is, I would say it's sort of mixed, but if you're interested in individual trees and their future projections, there's a U.S. Forest Service website called Forecast that looks at current tree distributions and their current environmental preferences, and then under various climate scenarios, then comes up with their future distributions given the climate change is expected, and then you can start to see places where yellow would be places. This is for red oak, which is one of the trees you find here. Yellow would be places where it's here today and it's expected to be here in the future. green would be places where it's going to expand into, and then red would be places it might disappear from or climates would become less favorable for. And so it's comprehensive. It's got almost any tree species you can think of if you've got a tree species of interest, but it's not the most user-friendly website. You have to kind of search around a little bit, but it's all there, so you can dive into it. Okay, so just to kind of sum up again, just kind of sum up where I began, that we have seen these profound transformations driven by past climate change. Ecosystems transforming like a devil's lake over and over again over the last tens of thousands of years. The ecosystems we think is stable around us are incredibly dynamic and changing all the time. And yet through that, biodiversity persists. Most species persist their way through. We can see that species adapt by moving across landscapes and persisting in particularly important refugial landscapes like the driftless area, and that we can help species adapt by slowing down climate change, accelerating rates of adaptation, protecting key areas, and doing the science. So, all right, so I'll stop there and just give thanks to you for spending your time here today. Thanks to Badger Talks and the National Science Foundation, which has been the primary funder of this work, and then a whole bunch of colleagues in my lab and around who participate in this work. So thank you for your time and attention. I'll take questions.